All right, question one. So let's start by looking at Q1, and we're looking at that point P. So here we have a positive, and we're going to treat that test point as a positive as well. So it's going to be a repulsive force. So that means because it's a positive at Q1, it's going to be an E1 that's pointing straight up. And inversely, we're treating that point P as a test charge as a positive. Also, we know it's going to be pointing towards Q2 because it's negative. So like these positive to negative attract, and then positive and positive repel. So we'll call that E2. And the other important thing here is we need to find that R value, right? So we have R1 is given, right? So that's 6 meters. And we know this value right here, but we don't know anything about, let's just call it R2 from here to here. Well, you can solve for R2 just using Pythag. So R2 is going to be equal to the square root of 6 squared plus 2 squared. R2 is going to be equal to 6.32. So at this point, we have enough to solve for the E net. So let's start off by writing our primary equation. That's going to be E net is equal to the sum of the electric field in the x direction squared plus the sum of the electric field in the y direction squared, and we're going to square root that whole expression. We need to first find E net x, or whichever one you want, but I'm just going to find E net x first. We look at our field that's acting here, right? So E1 is pointing straight up vertically. Let's draw a coordinate system. It's pointing straight up vertically, but E2 is on this angle, right? And if you remember from 135A, with these things that are at an angle, we need to break it into its components. So that means for E2, we have an y component pointing downwards. Let's call this theta right here. So that's E2 touching the angle theta. So therefore, it's going to be cosine. And then we have this other guy right here pointing in the x direction, E2 sine theta. Okay. And then just to find theta right away, we can just say tan theta. We're just going to look at that opposite over the adjacent. Theta is equal to 18.43 degrees. So this should be pretty much review from last semester. Okay, we know our equation. That's KQ. Which one are we talking about? 2. That distance between them, that's R2 squared sine theta. We already found what theta is. You just plug everything in. K is that constant, 9 times 10 to the 9th. And then they gave us the charge. We found R2. We multiply by sine of the angle. We just found what the theta is. So that's equal to 213.71 newtons per coulomb. That's E net x, okay? And then looking at E net y, we have E1, which is pointing in the vertical y direction, and then we have E2 cosine theta, which is pointing down in the opposite direction. So this is what I mean when I say vectors, you get your sign from the direction that the vector is pointing, right? We define positive as going up, so that's why E1's positive. However, this E2 cosine theta is pointing downwards, so that's why we're going to plug in minus E2 cosine theta. At this point, it's very similar to what we just did. We just got to plug in everything. So K, what's the charge there? 1 divided by R1 squared minus K, what's the charge there? 2 over R2 squared cosine theta. Factor out K, that just makes it a little easier on you when you're plugging into your calculator. Okay. And this whole thing will be equal to minus 391.3 newtons per coulomb. Okay, so now we have our x and we have our y components. At this point, we can build the E net like triangle, right? So our E net x, that's that 213, is positive. So it's going to agree with our coordinate system in the positive direction. Let's call that E net x. And our E net y is negative. So that means it's going to be pointing downwards, right? So that's like tail to head vector addition from 135A. And now we just have to connect this tail to head, and that's E net. And let's call this angle right here theta prime. Okay. Again, we talked about how to solve for E net up here. So you just got to plug everything in, do the square roots, end up solving for E net is going to be equal to 445.5 newtons per coulomb. Okay. But we're not done yet because we need to find the direction. So to find the direction, let's just do the tan function. So tan theta prime is equal to E net Y over E net X. Theta prime is equal to 61.36 degrees. Still not done. It's going to be below the positive X axis, right? Because this is the positive X axis, and we're going to be just that amount below. Sorry. Still getting used to the iPad handwriting, so it's unclear. All right, any questions on this one? This one, you guys got to be bulletproof on this because it's going to either be a field or a force in solving this exact way. Cool?
For example, for sine will be opposite of the hypotenuse instead of finding the angles. Do you have like a specific way that you recommend,
or you can do either one? Yeah, I just like to find the angle. I think it's cleaner, but if you're comfortable the other way, do it. Yeah, that's fine. All right, anything else? Cool. And I guess, like, just to be clear, like the electric field will always point the direction a positive charge would move, right? So if you have these parallel plates and you have like plus on one side and minus on the other, it's always the direction a positive would move. So it's kind of the point there. All right. So question 2, we have the same configuration of charges as in question 1. We want to determine the net electric potential at point P. Okay, so we're solving for that electric potential, that voltage of a point charge. That's equal to KQ over R, right? And KQ over R is in units of joules per coulomb, but voltage is how we solve it, right? That's just another way to write that. And it's a scalar value. So that means when you see a negative, right? For instance, Q2 right here, this guy's a negative. That means you plug in the negative for the charge. It's a scalar. Forces and fields are vectors. Voltage is a scalar, just like how weight is a scalar, right? It is the number that it is. And I think that this one we should also be comfortable with, and let's just run with it. So same diagram. I'm just gonna copy this. Copy. And also, if you have questions, just feel free to interrupt. Oh, geez. Sorry. All right, I'll find a better way to do that next time. So I think that it's a good idea to just label these again. Let's call this R1, and we'll call this R2. We already know what R2 is equal to. So we're asked for electric potential. We're solving for the voltage of a point charge, or just VP, right? Let's call it VP. So VP, what is that equal to? Well, we know what the potential is there is going to be interacting with the charge at position 1 and position 2. I'm sorry, which charges 1 and 2. So that means VP is equal to V1 plus V2. Our equation for this again is KQ over R. So that means it's going to be KQ over R1 and then KQ2 over R2. Let's factor out the K. Just make it a little cleaner. And then we can plug in our charges. Let me write what K is too. 9 times 10 to the 9. And then R1 is 6. And plus, I'm going to write minus over here, just to remind everyone that when we see the minus charge, we plug in the minus. And if anyone forgets that on the exam, you're grounded. Okay, so you solve for VP, and VP comes out as a negative value. So that minus sign is like a quick way to mess these things up, especially when you're going fast. I just remember forces and fields, they're vectors. You use the directions of the arrows, and then the other guys are scalars. Okay, yeah.
So for scaling, you plug in the minus sign, and for force and field, you just deal with it later?
No, you look at the diagram, right? So like this one right here is pointing downwards. We define this as upwards. So that means when we plug into our equation, that's when we recognize the negative.
So that's how you deal with vectors.
It's with vectors.
But what we're doing now is a scalar.
This is a scalar, so right off the bat, it gets plugged in. And then part 2 here, someone actually emailed me about this, and this is an equation that's on your equation sheet, but he never talked about it in lecture. And it was actually on my midterm when I took the class, and it's also on the practice ones too. So I think it'd be worth recognizing. And I'm going to show you kind of the trick to it. But first, let me talk about it. So the third charge, and that charge is -5 microcoulombs. I forgot to write that on the sheet, but that's -5 microcoulombs, is placed at point P. What is the total electric potential energy of this system of 3 charges? Okay, so the key words here are total electric potential energy. And then when you see systems of these 3 charges, you need to think in terms of total potential energy. So what that is actually is the total work. And you can represent that by, potential. And that's going to be equal to the sum of every charge interaction. So what that basically means is the total work is the total potential energy it takes to move like all the particles we're talking about here. So that's going to be this guy, and this guy to where they are now. So it means it's like a multi-system interaction. So what does all that mean? Let me write the equation first. So it's going to be equal to the sum of each charge that's interacting and then the distances that are between them. So you can call that I, call that J, and then the distance between I and J. It's kind of a weird looking equation, but let's see how to do this. So let's draw our triangle again. There's a way to, oh, there we go. So over here, we have Q1. This is 6 meters. Let me do a different color. 2 meters, and that was at 6.32. Okay. So what we're doing here is the total potential energy it takes to assemble these particles where they are now. And we're dealing with this system of charges. So first is we have to recognize the combination of charges, right? Because each charge is going to be interacting with one of the other ones, right? So Q1 is going to interact with Q2, just as equally is going to interact with Q3. So when you write out the equation to figure out which I and J and their distances between them, you need to figure out how many combinations there are. So to calculate the number of combinations, what you're going to do is take, so I'm going to say number of combinations is going to be equal to n times n plus 1 divided by 2, where, and I'll call this part 1 of question B. All right, let me finish and then we'll, where n is equal to the number of charges, and then subtract that by 1. So in this case, how many charges do we have? We have 3, so -1 is equal to 2. So that means 2 plus 2 plus 1 divided by 2. That equals 3 combinations. So what are these combinations, right? Well, that's going to be equal to, well, I think it'll be easier if you see it, right? So U total now is going to be equal to K. Q1 interacts with Q2. And the distance between them is, let's call this X, let's call this R, and let's call this Y. Divided by X. Another combination is K Q1 interacting with Q3, and that's a distance Y between, so we've seen 2. And the third instance is K Q2 with Q3 over R. Okay, so with 3 charges, there's only going to be 3 that you plug in, but you could see how this exponentially grows by adding another charge because the number of combinations like shoots up in a linear way, right? Because we know one of the combinations is 1 with 2, another combination is 1 with 3, and the final combination is with 2 with 3. But if there's a fourth one, there's another one of those added to each one. So you could end up getting this very long expression. That's why this calculation right here of the number of combinations is a good way to start, because otherwise you can miss one out that you didn't even consider, especially when it gets to 5 charges. I think that was the example. There was 5 charges, and that takes a long time to solve, right? Especially if you like forget one. Does anybody know which example I'm talking about? It looked like a square with another charge in the middle. Yeah, like that one can, like if you, like you could easily miss one if you don't recognize all the combinations. And then at this point, it's really just plug everything in. I would recommend factoring out K. And then it's just the fun run of plugging and calculating. And I'll leave that to you guys, but what it's going to be equal to. There we go. Okay. So any questions on that?
Yeah, I guess my only kind of concern is that like in the solutions for that problem you're talking about, it said 1/2 some of the cookies,
It says what?
1/2. They see that like 1/2
Mm, that's a different equation. What's the one to the right of that?
It's for capacitors. It's also says 1/2.
I mean, that's the equation for this one.
Is that on the sheet?
I don't know.
At least like in the answer sheet or in the answer like solutions, you put 1/2 times the sum of Q times the B, which is equal to that.
I mean, I would need to see the question, but I like that's the right equation for this. Because you're treating each one as KQQ over the distance between them. So there's no 1/2 in that expression. Yeah.
In this one, would you include the negatives for any of the charges or no?
Let me see. Yeah, I think, yeah, you do include them. Yeah. So like Q3 was a negative, you'd plug in the negative.
Where did we get the value for Q3?
Like I said, I forgot to write it on the sheet, but it's equal to right here, -5 microcoulombs.
Thank you.
Sorry, I have a question about that. So on the equation sheet, it has the equation for system of charges, and I think like what they asked earlier, it has the 1/2. So are we not supposed to use that equation?
Let me review that question and I'll make an announcement because I know this is the right equation for this.
All right, thank you.
I need to think about that. All right, let's just move on. I can't think of why they would have the 1/2 there, but it's fine. Amelia, can I see the question? Oh, they're using the
Or it looks like.
can I see?
Oh, it's the example.
Oh yeah, so it's a different type of question.
Oh,
Yeah,
I
yeah.
see.
How is it different?
So what we're solving for in this one, let me use the exact words. We want to determine the total electric potential energy, right? So to solve for the total electric potential, you need to look at the interaction between every single charge and you just add them up. Yeah.
But then this one's different because it doesn't have potential.
Yeah, because you're just looking for the energy. of the system
But
now.
then they include the U, they're referring to potential energy.
Yeah, I know. That's why I was confused. When someone emailed me, I was like, wait, that's the same thing.
So I was reading the book, so it's something about like you take the average work done in the system, so that's why the 1/2 is there.
Yeah, I'm not sure about that.
And we can, I guess we can.
Yeah, I need to think about that a little bit more. Okay, so let's look at question 3 now. Here we have 3 charges at the corners of an equilateral triangle. We want to determine the net force on the -4 microcoulomb charge there. So there's 2 ways in which we explore this electric force, right? That can either be the point charge form or the electric field form. So the point charge form is the one we just kind of looked at, where it's that Q over R squared. And, K is that Coulomb's constant. And alternatively, if we know the electric field at a certain point, we can use the F equals QE equation. I think we went over that in one of the worksheets. So let's start off by drawing our diagram here and everything that we know, because this is an equilateral triangle. Okay. So this is Q1. Okay. Minus. All right, so it's an equilateral triangle, so that means we know all the sides are equal. And the angle there is always 30. I'm sorry, 60. And then we're going to draw each vector here. So let's start with the effect of Q1 on Q3. And how's that vector going to look? So like the effect of Q1 on Q3.
It's sort of point to the left down.
Yeah, one second. Let me relabel this, 'cause this doesn't make sense the way I labeled it. Let's do this. It's just going to point down on the same angle there, like that. We'll call that F3. And what about Q1 and 2? Yeah, it's going to be attractive because it's a minus going towards positive. Let's call that F2. Okay, next thing all we got to do is break this down into its components. Hey guys in the back, please stop chatting. So that's going to be equal to F3 cosine theta, because we're touching that angle theta. We will call this theta right here. Okay. So at this point, this question should be nice and familiar. We're going to be solving for F net, which is going to be equal to F net x squared plus F net y squared. And we're just going to need to plug everything in. So let's just start with the sum of forces in the x direction. We look here. We have F2 pointing to the right, and we'll say that's in agreement with our defined positive direction. We have F3 cosine pointing to the left. So that's going to be the negative there. So we'll say F2 minus F3 cosine theta. What's F2 equal to? Well, that's going to be K, my charge that's interacting with the other charge, so Q2 and Q1, divided by the distance between, that's that R squared value. And then minus K, Q3, Q1, divided by R squared cosine theta. At this point, we can just do some factoring out. So we can factor out K, we can factor out Q1, we can factor out R squared. And what we're left with is Q2 minus Q3 cosine theta. Okay. So plug everything in, and what you'll end up getting is 0.009 newtons. Oh, that's not it. Okay, and then now for F net y, let's see what we have here. We have only one vector, and that's the y component of F3. So that's F3 sine theta. And it's going to be a minus because it's going against what we defined as positive. Plug everything in. And that's going to be equal to minus 0.047 newtons. Okay. We can now draw our FNet diagram. Oh my goodness, why do I keep doing this? And we'll see that we have a negative for our X, so that means pointing this way, and then same thing with our Y. So it's pointing downwards. We're just going to connect them. Here we have our FNet. Plug in, we already know the equation to roll with. FNet is going to be equal to 0.048 newtons. We're still not done. We need to find that angle. Let's call it theta prime. Theta prime. Theta prime is going to be equal to 79.15. And then how can I specify the direction of that vector? What would you guys call it?
Minus that graph.
Yeah. Or you can call it, let's say, like west of north. What did they call them in 135A? You guys remember that? What's that?
South of that.
Yeah, that's right.
Oh, that's so cursed.
Yeah, that's all. I hated that. Yeah. I'm sorry, Keith.
If you just left it like negative and didn't put like the direction, would you get like marked off and?
Wait, like if you just left this?
Yeah, or like, for example, like for number one,
Uh-huh.
I think the theta was like when I put in my calculator, it was like negative 61.3. So if you just left it negative 61.3 and didn't say like the direction like below
That honestly, I don't know. Like to me, that seems weird. Like I wouldn't report a negative angle, but I don't. I would say to be safe, no, but I don't know the details on that. Sorry. Yeah. But when you solve for like a trig function, you don't plug in the negatives normally. Yeah. But it's fine. Okay, so now, like before, I think that's stuff we should be pretty comfortable with. Like this is where it gets more fun because it gets a little bit more involved here. So Kirchhoff's, this is going to be on the exam 100%. There's two scenarios that you use it. Like you'll see this, you have to use it. If you have batteries in parallel, or if you have resistors and capacitors that are in the same circuit. It's the only way to simplify those through the tools we have. I think namely, if you see batteries in parallel, like you got to do that. You got to use them. So I know there was like a little bit of confusion before because I do a slightly different way and each professor does a slightly different way. So just pick your favorite, pick the one you're the most comfortable with and just roll with it. I'm just going to do my way just because I think it's the easiest. So let's put this diagram in here. We want to determine the current through each resistor in the circuit that's shown. Okay. So we're looking for I1, I2, and I3. Let's first start off with how I like to approach these kind of questions. I identify the junctions, call this one A, call this one B. And then I look for my biggest battery. I start on the minus, I start on the side, the plus terminal or the minus, whichever one you want, of the biggest battery. And I draw the current, like leaving that way to a certain junction. Let's deal with junction A. So remember, here's our plus terminal, the battery, here's our minus. This is the 20 is bigger than all these other guys. So I start behind that and I write the direction of the current that it truly goes. And we'll call that I1. I then go to the next biggest battery and I look at the minus, I look at the plus and minus terminals and I'm like, okay, which way would the current truly go? It goes from minus to plus and I draw the current going that way. So let's call this I2. And then I go to my smallest battery and I do minus to plus. And you know what? This time it happens to work out nicely that the current can truthfully go this way, right? Because it does go minus to plus normally. So it can actually go that way. But it's not always the case, right? Like this could have easily been let's say, now this is the hypothetical scenario. This is the plus terminal and this is the minus terminal. The currents that go in need to be equal to what goes out. So that's why it's most likely to go that way. How I kind of think about it is Like imagine these currents are like really strong water currents, right? What's more likely to overpower the 2 current is the 20 current and the 18. And that's why I'll be able to like overpower what's the typically defined direction. That's kind of just like a weird way. But the other like fact of the matter is it doesn't matter which way you guess as long as what goes in is equal to what goes out. So everything I just guessed, like this one pointing clockwise, this one pointing clockwise, and this one pointing clockwise, I could have done them all the inverse and it would have been fine. Okay, let's call this one I3. So let's start with our junction equation. So what's our junction equation? And let's do some loops. So let's see. I'm going to do an inner loop and an outer loop just to show that we could do both, but you could choose any combination that you want. So let's do I1 down there. And by definition of the loop equation, that change in V is going to always be equal to 0, right? So we'll say 0 is equal to, I start behind the biggest battery. So that's a 21. I always like to start behind a battery so I know when I completed my loop. And since the direction of the current here for I1, the direction of the current is this way. Let's all agree on that. And what we define as our loop, which is going clockwise, are in the same direction, right? Our current's going this way and our loop is going this way. We can write positive 20. After the 20-volt battery, we hit the resistor. Because our current is going through the resistor clockwise and our loop is going in the clockwise direction, we write -5. What's the current there? I1. Oops. -5, I1. And if you have a good eye, like the whole thing of this, the whole thing of this equation here is that delta V is equal to 0. What's R times I? That's equal to V. So that's kind of how that whole thing works out. And then we're going to keep moving along. We now hit this position. Here, our current is pointing this way and our loop, so our current is pointing this way. Our loop is kind of bumping into it with respect to the direction of the arrows. So that's why it's going to be +3 I2. So not like this scenario where the current and the loop are going the same direction at that point. Here, the current's going this way and our loop's going this way. So they're pointing opposite directions, and that's why we put the plus in there, where previously we did the minus. We keep moving along. The next thing we hit is our battery. This time, our loop hits the plus terminal first, so that's why it's going to be -18. Previously, our loop would go through the minus, then the plus terminal, but now in this case, we're going to go through the plus to the minus. So that's the difference between our signs. What's up? Yeah. Okay. So our current down here is going this way. We agree on that. Our loop here is going like this. So if we imagine our currents like this, our loop is essentially going like this. Because the current and the loop are going in the same direction, you plug in a -5 and then whatever the current is there. Alternatively, up here, our current's going this way and our loop is going this way. You see how now the arrows are kind of like crashing into each other? Because of that, we plug in a positive here. Yeah, but be clear that that's when we're talking about resistors because it's a different with battery. Yeah. Okay. We're all good on that? All right. And then what I do next, like I'm literally showing you just how I would, like on my exam, this is how I would do it. This is loop equation 1, 0. Condense the equation as much as you can at this point. Okay. And let's do loop 2 now. I'm going to do an outer loop. And also by preference, I like to use the biggest battery in both my equations, but that's just like what I want to do. You could easily do this loop or whatever. And I also find it easier like to have to make sure your whole equation is going to have like that positive battery value. If you agree with the minus and plus terminals, like I said, remember when you go through your loop minus to plus, it's going to be a +20. And if your loop is the other way, it'd be a -20. And for some reason, minuses make me confused. So I like to use the positive. So that's just another thing I like to do. But there's really like, it's really your game. Okay, so loop 2 now. And this time you guys can kind of call it out. So I'm starting behind the 20, so that means 0 is going to be, what's the sign there? It's going to be 20 plus or minus? So 20. What's next? Minus 5i1. Next. Minus 2i3. Next. Next. Plus 2. Why is it plus 2? Yeah. Everybody see that? So now you just got to clean up this equation. You'll have 22 is going to be equal to minus 5i1. And then what's that? Minus 2i3. Okay. So it's what we're going to need to solve in terms of is we're going to know what I2 is going to be equal to, and we're going to know what I3 is equal to, because in both equations we have I1, right? So that means when we plug back into our junction equation, it'll be everything in terms of I1. So to get everything in terms of I1, we need to isolate our variables of interest to one side. The first thing I'm going to do, just before I even do all that mixing around, is just get rid of these integer values that are in front of our variables that are going to be modified. So I'm just going to divide up here everything by 3. So 0 is going to be equal to 2 over 3 minus 1.67 I1 plus I2. And then here it's going to be 11 minus 2.5 I1 minus I3. Okay? So now when I rearrange these equations, I'll see that. Let me first bring this guy down. Get I3 onto the same side here. So that equal to 0. And what's I2 equal to? Well, now all we have to do is just move some things around. We'll say I2 is equal to 1.67 I1 minus 2 over 3. And then I3 is going to be equal to 11 minus 2.5 I1. Now we know what we can plug in for I2. We know what we can plug in for I3. So at this point, all we have to do is, move everything in. Then plus, oops. Oh yeah, so we have a minus I3, so make sure when you plug everything in, you adjust the signs. And that whole thing is equal to 0. You can now you can clean this up, solve for I1. I1 is going to be equal to 2.26 amps. Okay? And I like having these equations up here all written out, because now I can just easily plug in I1 right here, plug in I1 right here. I can easily solve for I2, which is going to be equal to 3.11 amps. And then I3, which is going to be equal to 5.35 amps. Okay, so the kind of nice thing about the trick that I use to define the directions of my currents is most of the time your current values come out positive, but that's not always the case. Hypothetically now we're in fantasy world. Let's say I2 was equal to minus 5 amps. That doesn't mean you solved wrong, but that just means your guess was wrong of the direction the current is going. So we see here how I2, is going this way. So if you thought about it in a circle, that would be moving clockwise. So if I2 is equal to minus 5, you would say something along the lines of, guess was wrong, I2 equals 5 amps, current is counterclockwise. Whereas before we just, based on our guess, define it this way. But like I said, like the way I normally set this up with starting with the biggest battery and working that way, normally your guesses are right. But like I said, it's still just a guess. Okay. But in this case, lucky us, the guess was right. And we're able to solve this pretty cleanly. Any questions on this? Like this is like probably the level, maybe like another resistor or two that you guys will see, but. I mean, you could really have done whatever you wanted. I like to use the biggest battery in both of my equations, but there's like no other reason.
Oh, if you flip the 2 volts like you did earlier,
Yeah.
Solution, you would still draw the current this way.
Yeah, because what goes in has to equal what goes out. And my logic is like, if this is the strongest water, this is the second strongest water, this would be the weakest one going this way. So it's more likely to be overpowered. So that's how it could work against the direction. It's kind of like a weird thing, but that's kind of it. All right. Anything else on this one?
I'm just gonna follow your algebra to the, for the coordinate again, I got a slightly different number.
It's okay. It might be a few decimals off.
Okay, I got, I1 is 2.5.
I mean, like that, I would need to see the work,
Okay.
but I'm, yeah, I think this way is, I think it's solved correctly here. But it could totally be a rounding thing. They wouldn't care if it was off by like, even like a whole number if you're right, your numbers were right. Like, and your logic was right. Okay, so now question number 5. Question number 5 is a little more difficult and should be kind of reminiscent to the homework question. And the only reason I included it is because it has that capacitor in part C. Also, I made that diagram by myself on a website. So you're welcome. I'm gonna give you guys like 15 minutes to solve this one, or like 10 minutes to solve this one, because it's just such good practice. Just even if you can't do parts B and C, just do part A. And any questions, I'll be circulating, or ask your neighbors or anybody. You guys know what to do.
Batteries is like regular batteries that look different.
Yeah, those are actually true batteries. What we saw, like what the other one, like that right there is actually not a true battery, but that's beyond us. Don't worry about it. Don't worry about it.
You know what, what's the deal with ground is basically?
Like rounding?
Ground.
Oh, ground? That's like, you know, when you, within every outlet in the United States, there's a copper wire behind it and it goes straight into the ground. Basically, what you can use the ground for is like a point of zero you can work backwards and start loops from. It's not going to probably come back up. But it is like, on one of the homework questions, there was a ground and a switch type question. Because the voltage there gets dampened to zero, you can always start a partial loop going back from there. But like, that's pretty tricky, like, besides that question. Let me look 1 second. Let me plug in my laptop and come look. Are you serious?
Yeah, this is, I saw this one, on the recording, this report, but go ahead.
Yeah, so you're saying that.
Oh, no, you can just start at the button. Oh. Yeah, once you're down there, it's equal to 0, like, look, that's why this one said that you could really, put the classes in this, but the main idea is you can do partial restart. And you can use that to solve for the potential of it. Because like, where it becomes relevant is in the first 2 and 3, right? And, so to determine how much stuff, if you do a partial loop from either of it, you can, it's basically per pulse, but only from what's touching the loop to the point of the force. Oh, I don't know, recently. I don't know what I'm saying. So there's not just, there's 7 of the first one. Yeah, everyone's not the same exam. So I've never seen one of these exams with multiple choice, so I have no idea what that looks like.
So it's 7 multiple choice questions?
That's how we win.
Okay, yeah, and he sent me an email saying there'd be 1 multiple choice question. But that also doesn't, like, who does a 1 multiple choice question?
I'm gonna get over there. That's the process. Yeah. Okay, that typically ends up being like, it's chance. The question?
So, yeah, I can't really answer my way around the book.
Pretty
Like
sure.
goes straight.
You must be doing something wrong.
That means like, so. Yes, I probably have an equation. And. Let's see, I plug it in, so you got the I two as this. and I two as that.
Oh, yeah.
So I plug in. I1 plus equals 6 on I1 minus 2 thirds and. And then minus I3, so minus 1 and plus 2.5 I1 equals 0. So against I1s into like 1 I1, that's 3.5 I1, that's 4.17. Is that, no, that's not.
Yes,
That's what I messed up, because I can't do triple. Okay, thank you.
Oh, I didn't, so, see, this is really hard to see, I didn't get Q to be on the outside, so I went like this. Yeah, people realize. See how I did it on the outside? No, it doesn't end, it goes around the whole loop is like that. Yeah, you want that. Well, it isn't much. Yeah.
Okay, that's just, yeah, okay. That makes sense. So then it-
Okay, because the loop thing, the is usually next to, right? So you can't jump over, do you mind if I make sense? So this loop right here, for the same reason we don't consider the two volt one, for the same reason we consider this loop. Because here we only contract the part, and it's 5, and it's 2, and it's 2 volts, 5 here. And then down here, we start at 25, 3. No, that's not this code. Try the next. Next one's a little more tricky, but it's really good practice. Yeah. So this is what we're talking about. Remember, we're like direct, like one bit of water will power the other one. So we have 90, 85, 4. So 90 is a strong. So that was definitely going to be going the true direction of the current. 85 is also pretty strong. It's also the true direction. So that's the one that can break down. So if you go to yeah.
Yeah, so this one, I know you want to talk, so it's funny. So I know like you guys have more on this, and I know, so it's usually it goes on the content that they. Yeah, but it's a trick of like, sorry for it, it's just like no, like resistors here, but it just. Well, not going. Well, the food, everything that is. Oh, so. Minus 85 minus 5 I.
Learn my way, now we can this way, and I'm like.
2.
Be minus 90, and then minus 8 plus 5 minus 2.
Okay.
Okay. I don't know numbers. Yeah, I did. This one, I did it on my first worksheet. That's thank you for my. But it is a good one. This is definitely good. It's 97.
Yeah.
Oh, I signed really good. I would keep on. I guess.
Because otherwise it's like this, everything's gonna be, so the way equation, and this is such a small. It's gonna be nice. Yes, and that's at least one thing to go into the loop, and what has to. Like the future goal. Like these two go in, this cannot pass. This because the interaction between them is double. It's kind of weird, there's gonna be just like just a greater attraction between them, like potential between them not change, and there's gonna be some distance. I don't know. I think. Well, I think what the essential is basically on for the other. Yeah, for the potential, for the potential. Based off the other. But then you have the. Yeah, so the scale of height levels, so that makes sense.
That's why. Okay.
Yeah, that makes
Just trying to solve my own question.
Yeah.
Okay.
Okay. You don't like it that way. Okay. So you start behind 90. Is there a question? Oh, I'll read them. I don't know. I don't remember those. But I'll say them out loud. All right, 3 more minutes on this one and then we'll.
So, for, this part at least, 3 pi minus 1/4 plus I1 minus I2 is I3, and then.
Wait, but you have the I3 pointing in the same direction that the loop's going there. So that'd be -7.
It'd be -7, okay.
And you can't combine those resistors there. Because look, there's a 5 ohm resistor there that has I2. The 7 ohm only has I3, so you shouldn't have I1 in here at all.
So is it?
It'd be 7I, let me here. It'd be 7I3, and then it'd be -5I2.
Oh, but wouldn't I3 just be, well, for like I3 is equal to I1 plus I2, so if you were to like.
Oh, you're like jumping ahead. Oh, I didn't even think about it like that is what you were doing. That seems tricky. So you have to factor that in, and it's gonna be a system of equations. I wouldn't do it that way.
Yeah, because that's what I learned how to work that out. It's kind of like watching.
You can do it then, but then this is harder though. All right, are you ready to roll on this? All right, so if it's, sorry, I did dim it a little bit, so if it's too dark, we could make it brighter, but let me first just say the answers here. So I don't know how you labeled them, but one of them is going to be 3, the other one's going to be 5, and the other one's going to be 8. So if you got that, high five yourself. And honestly, if anybody wants to drive this whole question, you can, or I could do it. What do you guys want? All right, I'll do it. Okay, so we have this wonderful diagram that someone made, took the time to make. And the point I was making is like, you don't have to do this way if you don't like it. Like, I just think it's a little bit easier and it's faster. But do whatever you want, as long as it's right. I don't mind. Okay, so what do I like to do? Well, let's start. So part 1, we're going to look for the current through each circuit element. I like to start with the junction equation. So that's what goes in is going to be equal to what goes out. Let's label the junctions. Oh, I already did that for you. And I go to my biggest battery. So my biggest battery is this 90-volt battery. The current here, it's going to go from minus to plus. So that's the minus terminal. It's going to be coming out like this. So let's call this I1. Now let's look at our next largest one. That's 85 volts. Let's call this
I2. And here's kind of the example I was talking about. What goes in needs to be equaling to what goes out. So we can just draw I3 as coming out, going this way, I3. So that's like confusing, right? It's like, oh, this is breaking the rules of how a normal circuit direction works, but that's okay with Kirchhoff's. You could do that. And I typically have the weakest battery as the one that's experiencing that incorrect current, like I'm putting that in quotes, because like what truly is correct, we don't know until we solve.
What if these batteries are all equal?
Then you just go 50-50. It doesn't matter. Every guess could be wrong as long as you solve consistently. Yeah. This way is just a quicker way to be making sure you're getting the positive values. So it really doesn't matter. So don't get too caught up on it. Like, oh, I don't know which way is the right way. As long as you use your loop equation and are faithful to the direction you defined, you'll be fine. Okay. So what's our junction at point, let's go A. And that's going to be equal to I1 plus I2 is equal to I3. Okay. And let's do our loops. And we're actually going to do every loop, even though you only need 2. Or yeah, let's do every one. It's good practice. And I'm going to call this one loop number 1. 0 is equal to, I start behind the biggest battery, and it's going in the same direction. Let's call that plus 90. What's next? You guys do the rest of this. Minus 85. Plus 5I2. Minus 10 what? 10I1. Let's clean up this equation a little bit. That's going to be equal to 5 plus 5I2 minus 10I1. And I know I'm going to be solving this in terms of I1, so I'm going to want to get I2 alone. So I'll just divide everything by 5 from now and just kind of make my life easier down the road.
Do you think how you added by I2?
Okay, so I2 is going this way, right? The current that's going here is like that, right? And our loop is going this way. So if we draw this like this and our loop, we see that our arrows bump into each other. That's how it's the plus.
So why do you subtract 85 plus?
Because the rules for batteries and the rules for resistors are different. With resistors, with batteries, the current's going this way, the loop goes the right way, that's plus. That's not the case with the resistor where it would have been minus. So that's why. Okay, and then now let's do loop number 2. And I want Sam to drive this whole one because I know he knows. Okay. Start behind the biggest battery.
I'm doing like a big loop, right?
No, I'm doing loop number 2. Look at loop number 2.
Positive 85
Okay.
minus, oh, so, yeah, minus 4.
Minus 4, right?
Okay. Minus 7I3.
Correct.
Minus 5I2.
Exactly. Great job, Sam. Thanks. I want to see if I can get rid of that sign that says this meeting's being recorded. Oh, whatever, it's there. Okay, so I'm going to clean this up a little bit. Let's get that 81 minus 7I3 minus 5I2. And this one doesn't have any I1s in it, so this is not going to be an equation that I'm going to go on to use, but this was just the practice to show, so I'll just write like that. Like this was the practice to do another example, so practice. And then the real loop we're going to be working with here is going to be this loop 3, which is on the outside. Loop 3. Well, you would then need to solve in terms of I2, yeah. You could if you wanted to. And then this is loop 3. Who wants to lead loop 3? Okay.
Okay, so, if the battery and the current are the same way it's positive, so it's gonna be 90 plus, 4
One sec, think about that again.
The square's going to the right, like on the bottom of the loop, right?
So it's going like this. I'm sorry?
It's -4, right?
Yeah, Carlos, can you remind her why?
Because it's entering the positive.
Yeah, that's correct. The loop is hitting the plus terminal first.
So it's not what the direction of the current's going, it's not going.
Yeah.
Okay,
It's with the resistors, you have to consider both. With the batteries, you just do that.
okay.
So
-4.
-4,
Let's see, -7. And then
-7, what's the current there?
the current is to the right,
No, so the sign is right, but I can't just write -7.
-7, oh, sorry, what is that? 3.
I3, okay?
And then -10 I1.
Nice. All right, now clean this up a little bit. Okay, and I'm gonna need to solve in terms of I3 to plug in for I1, so I'm just gonna divide everything by numbers, by 7. So 0 equals 12.3 minus I3 minus 1.43 I1. Is there confusion right now? I'll pause, yeah.
So why is 7?
The -7? Okay, because our current here is going this way
Oh,
and our loop is going the same way. All right, any other confusion at this point?
so like 3 was going on instead. It'll be a positive side.
Yeah. All right, any other questions on this? All right, let's keep going. So now we can just use our junction equation to solve for everything else we need to know. So let's convert everything so we can solve. So that's plus I2 minus I3 equals 0. And now we know what I2 is equal to, or I2 is going to be equal to 2I1 minus 1. And I3 is going to be equal to 12.3 minus 1.43. Can I move this over? Minus 1.43 I1. Okay. And now we're just going to plug everything in. So let's get our I1s going. So I1 plus 2I1 minus 1 minus 12.3 plus 1.43 I1 is equal to 0. Work the same thing as before. You get I1 is equal to 3 amps. I2 is going to be equal to, you just plug in. And you're just going to plug in. And I2 is equal to 5 amps. And then I3 is going to be equal to 8 amps. Okay? Yeah.
So I got the right version of everything, but I guess that I see it in the section. But I'm like writing it into them, so I just write like the value.
Wait, so you had I3 pointing like this?
Yeah.
So that would be wrong. Because what goes in, by the definition of the junction rule, what goes in needs to equal to what goes out. So you need to have at least one direction pointing out of the junction. Yeah, that's what I was saying. Like sometimes the true direction of current is going to have to be wrong. But that's just like by nature of the question. So I'm guessing when you solve like that, you came out with a negative somewhere, right? Exactly. So you just like that would like be an unfortunate way to lose points because you know everything. So just make sure what goes in is equal to what goes out. You need to have at least one thing pointing out, right? That's what I have the I3 for. Yeah. No, you can like go either way. Yeah. I just what I like to do is I look at the direction, I look at the biggest battery, I find the plus and the minus terminal, and I just start my loop so that at least I have the positive 90. So my biggest whole number is a positive. Yeah, but it doesn't matter. Oh, I wrote 2 pluses, obviously this is the minus terminal. Yeah. Any other questions on this? Like this one, we gotta be bulletproof on, guys. So this is great practice. Yeah.
So look at the four-volt battery one, we don't care what direction the current's go, we just care plus terminal, minus terminal, and the direction of the loop.
In what context?
In, writing the loop equation.
Well, yeah, it doesn't matter because like you have to have at least one part of the current going out. So it doesn't matter if you hit the plus terminal first. Well, that's what tells you the sign. Is that what you mean?
So the direction of the current matters for determining the sign for the resistors. But the direction of the current doesn't matter for determining the sign of the battery, right? It's just like, is the plus to minus direction the same or different as the direction of the loop?
Yeah, like that's a good way to think about that one part of it. Yeah. So like when you're trying to find like what the sign of the battery can be, so you draw your loop. If your loop hits the plus terminal first of a battery, then it's going to be a negative. And if your loop goes through the battery, like the direction the current would, so from minus to plus terminal, it's going to be a positive. Okay. All right, so let's move on to part B. Did anybody get a chance to do part B? Yeah, that's going to be a partial loop. So how did I write this here? Let's see. All right, so starting from part B, we can do a partial loop because we're asked to find what's the potential between 2 points, A and B. So that means final minus initial. So starting our loop at our initial, which is B, we go towards final. Oop. I wish I had a better color here. I'll use red. From B to A like this. Okay, so it's basically Kirchhoff's, except only what's encompassed in the loop. So for part B, we'll say VA final minus VB initial. Let's look at our diagram here. So our loop goes through the 5 ohm resistor, the same direction as the current goes. So that's why it's plus. Oh, I'm sorry. That's why it's minus 5I2. Oops. And then we go through the battery. We hit the minus and the plus terminal. So that's why it's going to be plus 85. We already know what I2 is. So all you got to do is plug that in right there. VA minus VB is going to be equal to 60 volts. Well, no, because our loop is going from the minus to the plus terminal.
Yes, that's the thing for 85, where this isn't the loop supposed to move it plus first.
No, but when your loop goes from the minus to the plus terminal, you put in the positive value. Like, right? Like that's why this is plus 90 here, because our loop goes like this from minus to plus. Yeah.
Well, then, okay. It does not look like a plus to positive, so the-
Our loop is like this. So this is the minus terminal and this is the plus terminal. So we go minus to plus. So it's plus 85.
Clockwise or counterclockwise?
This is a counterclockwise loop.
Okay.
Yeah.
Listen, my loop was like really easy, you know, that negative 60, but that was
I don't know how you would get negative.
oh, because on my loop was from like, I went from A to B, so it's like a,
Oh, so you went this way?
yeah. And then a negative
Well, no,
60.
it's final minus initial. So your final position is A.
Okay.
Yeah.
So it's always gotta be from the final to the.
Yeah, like whenever you have a delta expression, like whatever, it's gonna be like, let's say like find the change between here and here, like A and B. That delta means final minus initial.
Okay.
Yeah. All right, so is that clear? Because it's whichever one's first is final. Like it's always final minus initial. Like this is, remember from like from 135A? Like whenever you have a delta, like, so this would be delta VAB, final minus initial. Yeah.
So if we don't know the clockwise, it's that we just would have gotten the negative result. Like minus.
If you went like this way?
Yeah.
I don't think you wouldn't have gotten the negative result. You'd have gotten the same positive one.
So, but it doesn't matter if we double.
It does matter which way you draw the loop because you need to go from B to A. You need to start from B and you need to end at A. That's why it's final minus initial. Your final position's A. And there was a question in the back? Okay.
So for partial loop it matters, like for one of the things in the first part of this problem, do you have drawn the loops the other way?
Yeah, for the partial loop, it matters which way you're going because we've defined what's our final position and what's our initial position. With the Kirchhoff's loop, you can draw whatever you want. Yeah. All right, any questions on this part? Or are we ready to move on? All right, let's move on to part C. So C kind of throws, this complicates this a little bit more because now we're going to have a capacitor in here. So a capacitor with that capacitance value is added between points A and B. What is the charge on the capacitor? Oh, actually, I misrepresented where B is. B is actually over here. I was wondering why that came up, but the same thing stays true, right? Because your loop equation will just go like this instead. And you only interact with these circuit elements anyway, so same difference. So now we have a capacitor between these points. So let's draw that in. Oops. Okay, so we know what the capacitance is there. It's equal to 3 microfarad. Like that. Okay, so now we can solve this using another loop. Let's call this loop number 4. Loop number 4. Okay, and what makes solving with capacitors just a little bit more tricky is just one more thing to remember, right? So what you need to do is arbitrarily just assign one of the terminals of the capacitor as plus and one of them as minus. So I'm just going to call this guy up here plus, this side plus, and this side minus. That's my guess. No idea if this is right. There's like no way to know. And actually, you don't need, I mean, if it's helpful for you to visualize, because it's a fully charged capacitor, we can actually have current going through it, but that's above the class. But we have current now going through it, so that's how we're able to use Kirchhoff's here. So we have this loop 4. We've guessed what the plus and the minus terminals are. Now let's solve the way we have been doing. So we start behind the biggest battery. In this case, within our loop, we only have this 4-volt battery. So, you know, we're going minus to plus terminal, so plus 4. Then we keep tiptoeing around here. We go past A and we hit this capacitor. With this capacitor, we interact with the positive terminal first. Our loop hits the positive terminal first. Therefore, we need to plug in a minus Q over C. What does Q over C equal? V. Remember that everything here is delta V equals 0. So Q over C, that's our voltage for this capacitor we're talking about. So our guess was plus terminal here, minus terminal here. We hit the plus terminal first, so minus QC. Had we done the opposite, you know, it would have been the plus. We keep moving along here. We now hit this 7 ohm resistor. You know, we're now going, our current here. Oh, this was I3 here. Our current here and our loop are bumping into each other. So that means, sorry, I got like the weirdest. It says Sammy's phone has a 20% battery remaining for continuity camera. I don't even know what that means. So then we have plus 7 I3 because our current here is bumping into the direction of the loop. Okay, so what do we want to solve for here? We're looking for the charge. So we're going to get QC onto one side, 4, and then it's going to be plus 7. We already solved for what I3 is equal to. That I3 is equal to 8. You're just going to get QC, and then what's that? 56. So I'm just going to write 4 plus 7 times 8. And they gave us the capacitance value, Q equals 180 microcoulomb. Our answer came out positive. This tells us our guess was good. The plus terminal is in fact closer to the point A. So you would say, so therefore, guess is good, plus terminal closer to point A. If your answer came out negative, then you know guess was wrong. The plus terminal is actually closer to side B. Okay? We're clear on that? That's kind of the one way we can, yeah. Yeah, then that way's fine too. Because you know the potential between points B and C, so you know the voltage drop through there. So that's another way. That's a good way to think about it.
Wait, I just had a quick question.
Mhm.
So why did we, I don't know why you, or if you said this earlier, but why did we do it to point B in the corner and not point B?
Oh,
like,
I when I was making this diagram, I put point B there.
Oh, okay.
Yeah. So that was my bad. So I was very excited about this, and I realized that when I was over here. But is this everything else is right though? Because yeah, everything else is fine.
Okay, great. Thank you.
Okay. So now we have these circuit elements, simplifying circuit elements. Question number 6. So we want to determine the equivalent resistance when the switch is open and then when it's closed. Okay, so the only thing, I'm going to let you guys solve this one on your own, but I want to write this so we're all on the same page. So resistors in series, so R and S, we just add them, we should know that, but they have the same current. Okay, now capacitors, so C in S, we do that inverse addition for them. They have the same charge. And then lastly, for resistors in parallel, so R and P, they have the same voltage. And then resistors in series also, I'm sorry, capacitors in parallel also have the same voltage. Okay, so that's just helpful to know. And now to measure the voltage across any resistor or capacitor, you know, V equals IR for resistors, and then V equals Q over C for capacitors. So now I'll turn it to you guys to solve for the two equivalent resistance values in the cases where it's open and where it's closed. So this one should be pretty clean to solve. It'll take like 15. Oh my goodness, the camera's on my phone is what's on. That's what it was saying. It's so weird. Disconnect. Okay, so for question number 6, part A, when there's an open switch here, we treat it as if it doesn't exist. There's like nothing here. So then by definition, these two are in series. We can condense. We now have them in parallel. Resistors in parallel, we do the inverse addition. This is kind of a quick way to do inverse addition between two circuit elements. Condense one more time, and now we just have two that are in series. We can solve for REQ of part A. Now looking at part B, we have a switch that is closed. Now that we have a junction separating two circuit elements, that means they're now in parallel. With them in parallel, we have to do the inverse addition for both of these circuit element pairs. We then get a diagram in which they're all in series. You do that long inverse addition, and you end up with REQ. So we have parallel up here and parallel up here. And for looking at CP prime, again, we just need to add them all up. And again, this is equal to 10 microfarad. And I put it in quotes because, you know, it's the condensed form and we're just going to be cleaning it up a little bit. At this point, we can redraw something like this. We have that 5 microfarad, and then we have these two right here. Coming back around like this. and we can relabel. So we have that 12 volts, we have that 5 microfarad, we have that 10 microfarad. And then what's the relationship between all these capacitors? Yeah, they're all in series. So what do we do with capacitors in series? We do that inverse addition. So 1 over CS is going to be equal 1 over 5 plus 1 over 10 plus 1 over 10. CS equals 2.5 microfarad. And let's just redraw it just for fun here. And we have that 2.5 microfarad, that 12 volts. Therefore, CEQ is equal to 2.5 microfarad. Okay, and then the fun part here is finding the charge through each capacitor that is connected to that battery. Okay, so with this, you always need to start by solving for QEQ, right? That's just where you need to start. So QEQ is going to be equal to CEQ times V, where V is that EMF, which is equal to 12. So 2.5 times 12, QEQ is going to be equal to 30 microcoulomb. And between that battery and that capacitor labeled Q1, they're in series there. So we can say that the charges are consistent, right? Capacitors that are in series, they have the same charge. So therefore Q1 is equal to 30 microcoulomb. Okay, so now we have to work back a little bit. Let's look at our first. We're going to need to find our voltage drops acting on each of these capacitors so that we can look at them in parallel. Because a capacitor that's in parallel has the same voltage for the reasons we talked about. So that means this guy right here, V prime and V, are going to be the same ones, which are up here, being V prime, and then V, V, V. So let's write this. So we know QEQ now. We know that capacitance at the, finger quotes, 10 microfarad. And what we need to find is that V value. So do a little bit cleaning up. It's 30 divided by 10. So V is going to be equal to 3. And then for the V prime, QEQ, and I'm just going to rewrite it but it happens to be the same thing this time. So it's going to work out nicely. And then V. So V prime is also equal to 3. So we know what V prime is equal to. We know what the capacitance of each of these capacitors are. It's all given. We found V prime. We found V's. We can now solve for the charge for each single capacitor just by multiplying by 3. So Q2 is going to be equal to C2, which is 4, times 3. So that's equal to 12 microcoulombs, sorry. And now for Q3, I'll just write the answers, but I'll say it. That's 4 times 3, again, so that's equal to 12. For Q4, that's going to be equal to 2 times 3, so that's equal to 6. And then Q5, that's going to be equal to 6 times 3, 18. Q6, 12 microcoulombs. Oh, God. Because that's 4 times 3. All right. This is, I would say, good exam level for this type of condensing a resistor. The one previous was to really talk about the switch and get us used to the language, but that's a little easy. I think number 7 would be more what we expect. Okay, that's it for the recording. Email me with any questions, and good luck. So I might have misspoke, or I just want to be double clear about this. Okay, so when you finish condensing the series or all the capacitors, you're left with this CEQ right here, this 2.5, right? And you can solve for the charge of this capacitor as QEQ, right? Because the voltage drop here is equal to that full 12. By definition, all capacitors that are in series have the same charge. So when you work backwards now, looking up here, you'll see that this capacitor is the constitutes this one, and this one. And per that reason, we can say that the capacitor right here, or Q1, is equal to 30. So let me be very clear about that. I'll say it one more time. We say this is QEQ, we solve for that. And then all the capacitors that make this guy up that being this 1, 2, and 3, all share this charge because they are all in series. And that's how we're able to assign QEQ is equal to Q1 in this situation. And then the rest was, as I said. All right, I just want to be very clear with question number 7, kind of the key idea here. So we have this QEQ that we're able to find here because we know what the equivalent capacitance here, and we know what the EMF is, and we know that Q equals C times V, right? So we're able to find that QEQ. By definition, any capacitor, that being this 1, 2, and 3, that are in series have the same charge. So that means across each one of these guys, they all have the same charge because they all combined make up this 1. With that understanding, we know the charge here, we know the capacitance here. So to find more information relating to the charge at each of these capacitors, what we'll need to do is find the voltage drop at either. And then all capacitors which are in parallel have the same voltage drop, and that allows you to find all the rest of the charges. So it's kind of a stepwise backwards solution. All right, that's it.